Greetings YouTubers and welcome to the Gear Bench. This video is part 1 in a series on backcountry water treatment methods. I wanted to start with boiling because it's considered by some to be the gold standard of disinfection. Your biological threats to backcountry beverages fall into 3 main categories. There are cysts like Cryptosporidium and Giardia, bacteria like E. coli and Salmonella, or viruses like norovirus or hepatitis A. For these, heat is an equal opportunity killer, and it's capable of very high levels of disinfection. Boiling, however, is rather time-consuming and fuel-intensive. In this age of cheap ultralight microfilters, there doesn't seem the need to bother. Well, here are 2 reasons why you might find yourself considering it. Number 1, filters can fail. If the gasket falls out, you might not be able to get a seal with your bottle. Drop it just so on a hard rock and the plastic housing can crack. And if your bag bursts, a proprietary filter could become useless. Or, if you filter too much muddy water, you can get clogged up. And of course, anything can simply be lost. I saw a video by one of the most experienced hikers I know. She inadvertently let her filter freeze during an unexpectedly cold night. An ice expansion can damage the hollow fibers inside, so she resorted to boiling all her water for days until the next town where she could resupply. But no matter how careful you are, there's reason number 2. You might encounter water that your filter isn't capable of handling. The New Mexico portion of the CDT, for example, is somewhat notorious for its less than desirable water sources. Halfway Anywhere has a whole blog post about it. And for the pleasure of hiking all day through the desert, you get to dip your bottle into a scum-filled pool of stagnant water kept in an old tire. Now, being fair, algae's not that big of a deal, but consider that many of these sources serve as stock ponds for grazing cattle. And that means this water is regularly doused with the saliva and mucus of countless slobbery, wet-nosed cows. Even so, though likely teeming with bacteria, it's still something your pocket filter may be able to handle adequately enough to prevent you from getting sick. But that's not the last level of gross that you may be faced with. As Average Hiker points out, some of those stock ponds are muddy puddles filled with cow feces. If even one of the animals that drinks and defecates in that water is sick, you could be faced with a viral threat that the average hiking filter isn't qualified to protect you from. Now, I'm not suggesting you start routinely boiling water for purification. I don't. I use one of these. But if circumstances conspire against you, boiling is the ultimate backup. So the purpose of this video is twofold. To take a skeptical look at the persistent internet wisdom on this topic, even if it's just for personal edification, and to make the process of heat purification as efficient as possible should you find yourself resorting to a secondary method. So what is the conventional wisdom then? Well, the government says, bring your water to a rolling boil for 1 full minute. And whether it's the Federal Emergency Management Agency, as shown here, or the Centers for Disease Control and Prevention, that advice remains the same. Often, like with the CDC, there is the additional nugget: at elevations above 6,500 feet, boil for 3 minutes. And this advice is repeated ad nauseum throughout the internet. Is it wrong? Not technically. Boiling for that long will definitely make your water safe to drink. So what's the problem? It's overkill. You'll be wasting not only time, but for the weight conscious, you'll also be wasting quite a bit of fuel. And pasteurization's been around since the 1860s. It's the process by which heat is used to eliminate pathogens at well below boiling temperature. And it has been thoroughly studied since then. It's in daily use by the food industry, perhaps best known for the processing of milk. The FDA's Grade A Pasteurized Milk Ordinance is basically the authority on pasteurization, and on page 92, Table 3 introduces a crucial concept, that of temperature versus time. The first thing to note is the temperature at the top. And look how low it is. You can achieve commercial-grade pasteurization at just 145 degrees Fahrenheit. And of course, the very next thing to note is the time. It takes a half hour at that temperature to get the job done. And I don't personally consider that a practical amount of time to purify water in the field, but if you've had to resort to backup methods for some reason, you might not have the choice. For instance, if your backup system relies on one of these emergency candles, depending on the conditions, these can fail to produce anything resembling a boil. In that circumstance, it might be important for you to know that you can still make water safe to drink. Now check out how rapidly the kill rate rises even with relatively tiny increases in temperature. Just 1 degree Celsius going from 89 to 90 degrees doubles the kill rate. And look at that pasteurization times we're talking about. At 191 degrees Fahrenheit, it takes all of 1 whole second. That's not too long to wait, is it? And then finally, direct your attention to that bottom entry. At 212, pasteurization is achieved in 1/100th of a second. So now reconsider the advice to bring your water to a rolling boil for 1 full minute. To pasteurize for 60 seconds when it only takes 0.01 seconds is 6,000 times longer than necessary. I think it's fair to call that overkill. But in fact, it's even worse than that. You see, water can't just snap to a boil in an instant. It obviously has to be heated, and at every degree along the way, above a certain minimum, it is pasteurizing as it goes. So before it was 212 degrees, it was 211, and before that, 210, etc., etc. As you can see, just by adding the cumulative effects of the non-consecutive temperature points listed in Table 3, you'll be over-pasteurized way before you get to a boil. When you're using a stove, fuel is consumed per second of burn. And clearly you can save both time and weight while still enjoying a luxurious amount of safety by stopping somewhere short of the traditional rolling boil. Okay, but before we continue, some caveats and conditions. I've been discussing drinkable safety in terms of pasteurization, under the implication that it either is or is not. Well, this implies the fallacy of a false dichotomy, so I think I'm going to have to call one on myself.
Warning, bullshit alert!
Water isn't unsafe until some arbitrary line is crossed, beyond which it is simply considered safe, any more than it's cold until some point at which it suddenly turns hot. Just like temperature, water safety comes in degrees. In the case of water treatment methods, those gradations in safety are usually enumerated in something called log reduction rates. 1 log of reduction means the removal of 90% of a given contaminant. So for every 100 particles in a volume of unfiltered water, there would be 10 remaining after treatment. A 2-log reduction removes 99%, leaving only 1 particle. As you can see, a doubling of the log reduction actually results in a 10-fold decrease in contaminants, and the effect is logarithmic, hence the term log reduction. And this whole scheme keeps on going right past the decimal point, so a 3-log reduction is 99.9%, and on down it goes. So the question that should be boiling on everyone's mind is, what's the log reduction standard for commercial pasteurization? Well, according to the Codex Alimentarius, and no, that's not from a Harry Potter book, the Code of Hygienic Practice for Milk notes that pasteurization is designed to achieve at least 5 log reduction. So that's 99.999%. So far, so good, but bear with me. It's going to get more complicated for a bit so you can appreciate all the factors involved, but it will be surprisingly simple to deal with in the field by the end of the discussion. Looking at our pasteurization table again, although it has several temperature steps listed, there are actually more gaps than data points. You might think, I just need one number, a temperature with a practical pasteurization time, and I'll just use that. But in the interest of maximum efficiency, we would ideally have log reduction values for every degree Fahrenheit, and I made a chart to help explain why. And this is what I call a time temperature profile. I heated a ½ liter of water, which is enough to make most of your freeze-dried meals, in a titanium pot on a Pocket Rocket Deluxe. I chose a target temperature of 180 degrees Fahrenheit just as an example, and then I measured the temperature digitally every minute throughout the experiment. The resulting profile depicts the rise and fall in temperature over time. I started with water that was 52.8 degrees, and I achieved the arbitrary 180 at the 6-minute mark where I shut the burner off. Note the 3-degree bump after flame out. It's probably due to some residual heat in both the pot and the burner arms. Thereafter, you can see a pretty steady 2 to 3 degree cooling per minute as I let the pot sit. And this was in a 52-degree basement with no wind and no lid on an uninsulated pot. A key principle to be found here is illustrated by the red data bars amongst the blue. And water never just arrives at any given temperature. It has to travel there, and the process of heating and the inevitable cooling takes time. Knowing what we know from the FDA's table, pasteurization is occurring at some rate over a broad range of temperatures, but it's at a different rate for each and every degree. This means that above a certain temperature, microbes are being simmered into oblivion on a continual basis until such time that the water drops back below some threshold level. So the idea that you have to reach a certain temperature before starting your watch discounts all the pasteurization credits earned during the heating process, and perhaps more significantly, all the additional credits accruing during the ongoing pasteurization while your water cools back down. And for this graph, I chose a threshold of 150 degrees Fahrenheit. The red bars represent every minute spent at or above this temperature. What that gives us is not just some overly simplistic rule like 1 full minute at temperature X. It reveals a pasteurization kill zone that's 15 minutes wide. Right. Where did I get the 150 degree threshold from? Well, worldwide, diarrheal disease is the leading cause of malnutrition and second leading cause of death in children under 5 years old. It kills more than 500,000 young ones every year. So the problem is not a small one, and the number of people relying on adequate treatment is huge. The team over at Solar Cookers International includes scientists and engineers working to develop practical and efficient water disinfection methods for people in developing countries. Different microbes have different susceptibilities to heat, with viruses being among the most resistant. SCI provides this chart of rapid kill temperatures for the most common waterborne pathogens, and by killed rapidly at, what they mean is the temperature at which 90% of the microbes are killed in 60 seconds. That's 1 log of reduction per minute. This is sometimes referred to as a D value, or a decimal reduction dose. As you can see, 150 degrees covers you for all 3 types of pathogens: cysts, bacteria, and viruses. It also happens to fit nicely in one of the gaps in the FDA's table. 5 minutes at 150 degrees gives you the 5 log reduction of pasteurization. So going back to my example water heat, we can see that the red 15-minute kill zone would result in an extraordinary 15 log reduction. And that's at a minimum. The 1 log per minute rate is only for 150 degrees. We know that for every degree, the rate is different, and it goes up rapidly with even small increases in temperature. Most of those red bars are above 150, some of them significantly so. So clearly this example wasted fuel by providing more heat than is reasonably necessary. Alright then, so if we're trying to save as much weight as possible by heating just enough to get the job done without overdoing it, there's a lot we would need to know. First, you need the D values for each and every degree of temperature within a target range. But we don't have data that detailed. Just a handful of temperatures with large gaps between them. Then, you need both a stopwatch and a thermometer, so you can make an accurate time temperature profile like the one I did. And that's tedious and time consuming, and who wants to carry a thermometer in the field? And lastly, you would have to calculate the log reductions for each bar on the graph, adding them up to achieve your total amount of disinfection. And if that sounds like too much trouble each night at camp, I agree with you. It's part of the reason that the CDC and many others just make it easy and recommend boiling. If you search around enough, you can even get them to admit it. From the CDC's Yellow Book for Travelers, although boiling is not necessary to kill common intestinal pathogens, it is the only easily recognizable endpoint that does not require a thermometer. You just can't tell 100 degree Fahrenheit water from 150 degree water by looking at it. Now, if only there was some gadget that could tell you when your water was safe to drink. It should be small and lightweight, so you could drop it in a corner of your cook kit and barely know it's there. It should be indefinitely reusable but never need charging or parts replaced. And it should effectively do all the log reduction math for you, quickly and reliably in varying conditions regardless of water volume, starting water temperature, or altitude. No problem. Here you go. Allow me to introduce the Water Pasteurization Indicator, or WAPI. It's only 48 millimeters long, 9.1 millimeters in diameter, and it weighs a scant 4 grams, yet it does everything we've asked for. A brief history of the WAPI. In the early 1980s, Dr. Bob Metcalf studied solar water pasteurization and published a study in Applied and Environmental Microbiology. And in it, he concluded that if contaminated water were heated to 65 C, which is 149 degrees Fahrenheit, all pathogenic microbes would be inactivated. Fred Barrett of the United States Department of Agriculture worked with Dr. Metcalf on the solar cooker project. In 1989, he came up with the idea to use vegetable wax with a melting point of 150 degrees inside a tube placed in the water as an indicator. And then, in 1992, Dale Andreatta, a PhD candidate at the time in mechanical engineering at UC Berkeley, created the WAPI in its current form. It's a polycarbonate tube filled with soybean wax that melts at about 150 degrees. To use it, just place the WAPI directly in the water to be heated with the green blob on top. The tube size and the wax amount are designed such that once 150 degrees is attained, it will take about 5 minutes to melt completely. And once the wax all falls to the bottom of the tube, it ensures that water pasteurization conditions have been reached. Those 5 minutes give you that 5 log reduction we've been talking about. And that's it. Nothing to calibrate or adjust. Nothing to wear out or replace. After use, just remove it, let it cool down. And once the wax is solid again, use it over and over. It is both elegant and ingenious. And while the WAPI was designed to work with large volumes of water in solar situations, it's still perfectly applicable for use in 2 cups of water on a backpacking stove. To check this, I tested mine in 2 different ways. First, I just heated in a pot on my kitchen stove, and using a thermometer, I verified the water temperature and turned down the heat to keep it at a near constant 150 degrees. Sure enough, right at about 5 minutes, the wax melted and dripped to the bottom of the tube. Good. It works like it's supposed to. But what about in the field? The whole point is to not have to bring a thermometer. So you won't know when 150 degrees has been reached. There won't be any turning down the heat to keep it right at that temperature. What has to happen is you'll put the pot on and light the flame, and then you just wait for the wax to melt. And the water will be heating the whole time. And since the wax doesn't melt the instant that 150 degrees is reached, your water will keep getting hotter until it does. In other words, by the time the wax does melt, you'll have reached some temperature higher than 150. In order to find out what that final melt temperature of a continuous heat scenario ends up being, I ran an experiment in a glass beaker so I could watch what was going on. This was my setup. A ventilated space in my basement, no wind, 52.3 degrees Fahrenheit, and 70% relative humidity. I started with 50-degree water. The WAPI was set in about the middle of the water by elevation, and my temperature probe is on a clip so I can keep it away from the container's edge and also suspended above the hotter bottom. I aligned the tip of the probe to be level with the green wax. You'll notice the beaker's sitting on a rippled metal plate. I was worried about the glass cracking under the thermal stress, so I used a heat diffuser. I also kept the flame at a really low level to ease the shock of temperature change. The combination of low flame and diffuser plate meant a long time to reach melting point, over 13 minutes actually. Now, you likely wouldn't take that long on trail, and neither would I, with a titanium pot and a growling stomach. A faster rate of rise will result in more overheat by the time the wax can absorb that energy and fully melt, so providing even more safety margin due to the faster kill rates at higher temperatures. So think of this slow burn as a worst case scenario in the event your heating system is struggling with the current environment. Jumping forward, we finally hit 150 degrees at 11 minutes 6 seconds. No, the wax is still there, but it's just beginning to turn more translucent. And as the seconds pass and the degrees continue to climb, you may be able to notice the wax plug shrinking ever so slightly, and a tiny amount of green liquid has begun to pool at the bottom of the tube. Then, right at about 160 degrees, there's a sudden dump as the plug melts and the liquid drops. There's still a small nugget of wax clinging heroically to the top. Hang in there, baby! It lasts until 13 minutes 29 seconds, by which time all the liquid is at the bottom and the temperature is 165 degrees Fahrenheit. So what to make of these results? The time elapsed from melting point to full melt was 2 minutes 23 seconds. But it was supposed to take 5 minutes, right? Well, that was only if you left the water at 150 degrees. We got it up to 165. Okay, but what does that do to our pasteurization safety margins? Remember that the kill rate goes up exponentially with even small increases in temperature. Using this rate as an example, consider that the water in my experiment took 45 seconds to go from 161 to final melt. That's 3 full pasteurization periods at 5 log reduction each, meaning a total of 15 log reduction is achieved just in that portion of the heating. Higher temperatures vastly outweigh the effect of shorter times. So far from being dangerously minimal, it's more the opposite. We are arguably still overheating the water in this scenario. The goal was to save as much fuel as possible while reasonably assuring safe water. It seems to me that the best compromise is to shut the flame off when you see that first big wax dump around 160 degrees Fahrenheit. You're pasteurizing at about 1 log of reduction every 3 seconds at that temperature. And just the time it took to get there from 150 has probably done the job. But, just to be absolutely sure, you can let your hot water sit until the last of the wax liquefies. All time spent cooling down is fuel-free. Right. So speaking of fuel, you can't talk about savings without comparisons. I wanted to measure the difference in weight of fuel burned for a minimalist pasteurization versus the traditional rolling boil. For the pasteurization runs, I used the target of 160 degrees F. And as described, that's my ideal compromise temperature for flame off. And as I say, runs plural because I did 4, each at different level of flame. I digress, but this tip alone might be worth the price of admission for those looking to save fuel weight. I've watched a lot of stove reviews and seen a lot of pots boiled in basements, and in almost every one of them, efficiency is equated directly with boil times, and as such, they're usually running their stoves wide open at full output. But boil times are just a measure of speed, not efficiency, and only if you assume that heat added to the water per gram of fuel spent is the same across all flame levels, can you automatically conclude that a faster boil time saves fuel? Well, as it turns out, that assumption is not correct. Thermodynamically speaking, you're dealing with 2 competing effects. A higher flame pumps heat into your water faster, so you'll reach target temperature more quickly and can stop burning fuel sooner. But that higher flame also dumps heat into the surrounding environment faster as well. And that's an increase in grams of fuel spent that didn't go to heating your water. So, which effect dominates as you increase the flame to get there sooner? Well, intuitively, we should expect a penalty for our impatience, but that needs to be verified experimentally. Now, unfortunately, stoves don't come with a dial on them where you can set a specific amount by a number. If it did, this one would go to 11. So, I had to use subjective values like very low, low, medium, and high. My initial weigh-in was 723 grams. I used the large 16-ounce canister to minimize any differences in pressure between runs. Also, the stove in question is an MSR Pocket Rocket Deluxe, which has a regulator to maintain output across conditions. And I took measurements with the stove and canister attached, so there wouldn't be any fuel loss each time I unscrewed it and put it back on. For each run, I recorded the flame output so you get an idea of what that level looks like in real terms and the moment of attaining our 160 degree Fahrenheit target for the time elapsed. Heat number 1 was set to very low flame, just about a quarter turn from off. 160 was achieved in 5 minutes 15 seconds, and the weight after was 718 grams for a total of 5 grams spent. Heat number 2 was a low flame, maybe a quarter turn further open, and that got to 160 degrees in 3 minutes 38 seconds. The subsequent weight was 713 grams for another total of 5 grams spent. Heat number 3 was my approximation of a medium flame, and that put 160 F on the screen in 2 minutes 36 seconds, leaving 707 grams behind for a total of 6 grams spent. Fastest time so far, but now an extra gram lost for no additional heat in the water. And then lastly, heat number 4 was not all the way open, but what you might call nice and high, and that raced to 160 degrees in 2 minutes 11 seconds. And final weigh-in was 700 grams for a total of 7 grams spent. So look what happened there. The high flame used 7 grams of fuel to get the exact same 160 degrees as either the low or very low levels, which used only 5 grams each. That's a 40% increase in fuel consumption for no additional water temperature. And that seems to solve our earlier conundrum. A higher flame may add heat to your water faster, but it is less efficient because it wastes heat even more. So for fuel efficiency, stay away from the high end. And there would also be a set of dueling thermodynamic principles at the low end. Since you're heating water above ambient temperature, the pot will constantly be losing heat to the surrounding atmosphere, even as you're flaming it. So if your stove is set too low, the pot could cool off from the top as fast as it heats from the bottom. This could result in a bunch of fuel expended without ever reaching target temperature, and obviously that's not efficient either. So with too much or too little no good, somewhere there's a happy middle. And with the low and very low settings both using 5 grams of fuel, that suggests we're pivoting around that sweet spot, which is good because it makes it easier to optimize fuel efficiency given the subjective nature of the flame level. Just use something on the low end and you should be good. Of course, that's for my particular pot and stove. Further research should be done on other combinations. But we're not done yet. All the authorities tell you to get that rolling boil, and thus I ran heat number 5. I'm at about 300 feet elevation, by the way, but the 210 degrees Fahrenheit you'll see probably has more to do with the fact that my temperature probe wasn't touching the bottom of the pot. Time to boil was 3 minutes 11 seconds, and weight afterwards 690 grams. Total fuel spent 10 grams. Well, look at that. Using the conventional wisdom of a high flame to save time in getting to a rolling boil, you burn twice as much fuel as the skeptical method. Compared with a low flame to 160 degrees, you save only 27 seconds, but at the cost of getting only half as many burns out of your canister. To give you an idea of what that means in practical terms, one of the small containers will give you 11 boils on high, but you can squeeze out 22 pasteurizations on low. And then, just because I can't help myself, remember that you're technically supposed to boil for 1 full minute. Well, on high you're going through about 3 grams of fuel per minute. And that means a proper government-sanctioned heat treatment actually costs you 13 grams of gas. You only get 8 of those out of one of these, given the conditions in my test series. Okay, so there are weight savings to be had in reduced fuel consumption, but it's always fair to ask, what is the weight cost of the gadget in question? The original WAPI weighs 5 grams. Based on my test results, that's a savings of pasteurizing just 1/2 liter pot of water instead of boiling it. So if you bring this along and use it even once, it will have paid for itself by weight. And you can get these on Amazon for under $12. And just a reminder, I'm not sponsored by anybody for anything. I buy all my own gear at full price. I don't have any affiliate links, coupon codes, or kickbacks. There's also a slightly newer version called the Super WAPI. It's basically the same thing, but with slightly smaller beads at the ends holding the cable on. It weighs only 4 grams. These are also available on Amazon for a little over $10. To use them, you just slide the tube back and forth as necessary, so you can place it in your pot with the green wax up. Then you just drape the cable outside the pot to keep the WAPI in place. It's made of stainless steel, so your flame won't melt it. And then afterwards, all you have to do is reverse it. For a different take, there was a thing called the sports WAPI. The familiar wax tube comes in a plastic capsule without the cable. Instead, there's a magnet in the bottom. You remove the tube and attach it to the outside. Then the capsule acts like a buoy. You just float the whole thing inside your pot. And there are screws in each end, so after the wax melts to the bottom, you can flip it around and just use it again. And bear in mind, you'll probably need a good 3 inches of water to keep this off the bottom. It weighs 6 grams, but they don't seem to be making these anymore. I did find an Amazon listing for an updated version, the Sports WAPI 2, but that isn't currently available either. Other than that, I found one more style, and this one's from Sun Oven. It's another floater. No magnets this time. You just plug the tube into a hole in the bottom of the float. And this one's the heaviest at 11 grams, but maybe the ultralighters could use the extra space inside the container for their first aid kits. All good, but maybe you're still not quite there yet. You just don't want another gadget, even if it is only 4 grams. You're a tough customer, but I think I may still have something here for you. Let me see. Here it is. The Boil 3 Add 1 method. This method was cooked up by Tom Sponheim over SCI. We know that boiling water is a waste of fuel, but it's the easily verifiable temperature point you can identify without instruments. Well, having done so, you can add some of your cold, untreated water back into the mix. You'll quench the boiling water to some extent, lowering its temperature, but if you use the right amounts, your resulting mix will still be hot enough to achieve pasteurization. Mr. Sponheim determined that 3 parts boiling water to 1 part cold does the trick. So if you want a liter of disinfected water, boil 750 milliliters and then add the remaining 250 when you're done. Now, because the boiling point drops with altitude, you have to mind your height with this one. So to make it safe, the ratios were chosen for a worst case scenario of adding water that is just above freezing, and it will work all the way up to 4,000 meters or just over 13,000 feet, where the boiling point's only about 187 degrees Fahrenheit. Because these numbers were padded for safety at altitude, you're still going to be wasting some fuel if you camp near sea level. And for those folks, he gives you the special ratio of boil 5, add 2. Something for everybody. Well, part of the beauty of the WAPI is that it's completely altitude independent. Even on top of Mount Everest, the tallest mountain in the world at over 29,000 feet, the boiling point is still 161 degrees Fahrenheit, hot enough to melt the wax. It's also volume independent. It doesn't matter if you're making 2 cups of water or 2 liters, and there are no measurements to take or calculations to make. Either way, whichever you prefer, the choice is yours. Okay, well, that's it for the technical stuff. I thought I'd address a few of the usability issues that might come up. What's one of the big reasons people boil water in the backcountry? Making dinner, or more specifically, rehydrating dinner. And if you'll note, the packages always say to add boiling water. So the question arises, how good is pasteurized water at reconstituting dried meals? To test this, I brought my stove and pot into the kitchen so I could eat dinner with the missus like a civilized person. Set up my thermometer and put the flame on my patented efficiency low. I brought the water to exactly 160 degrees and carefully stirred it into a bowl of Mountain House Classic spaghetti with meat sauce. Then I covered it and let it soak. The official instructions say to add 1 3/4 cups of boiling water, wait 5 minutes, stir, and let stand another 4 minutes. Assuming that mine wouldn't hydrate quite as fully due to the lower temperature, I shorted the water 1/4 cup, adding only 1 1/2 cups instead. Now, I've never waited the prescribed 9 minutes like the package says. I always dig in after 2, maybe 3 minutes at most. So again, because of the lower temperature, I let this batch sit twice that long, and after 6 minutes, I had a look. Turns out, It was done. The noodles were soft and the sauce was moist without being runny. 6 minutes after adding 160-degree water, it was still hot enough to be above warm, but not uncomfortably so. And of course, your mileage may vary depending on how cold the air is where you're waiting. I was indoors, but you could always use a pot cozy if you're outside. I looked up what burning hot is, by the way. 160 degrees Fahrenheit is enough to give you second or third degree burns in under a second. So, dangerously hot. After several minutes, it should still be enough to give that nice hot meal sensation at camp. And I'll admit to being surprised at how well it worked. I like my pasta al dente, but I thought I'd be chewing my way through some pretty firm food. Instead, every ingredient in the meal had rehydrated just like it normally does, without having to wait 10 minutes for it to cool down enough so you can eat it without getting burned. Honestly, I can't see boiling my meals anymore. It's extra time and fuel for no better food. If you boil and I don't, I'll be sipping my after-dinner drink while you're still waiting for yours to cool down. That is, so long as we're talking about a freeze-dried meal. You see, not all adventure food is prepared the same. Mountain house meals are righteously freeze-dried. That means the whole thing's fully cooked first, and then it's spread out on a tray and frozen. A vacuum is pulled and the moisture is removed through sublimation. It's expensive and time-consuming. Not everybody does it. The bigger companies usually do, like Backpacker's Pantry and Alpine Air. And the advantage to the hungry camper is that freeze-dried foods reconstitute much more quickly, and as it turns out, they do so nicely at much less than boiling temperature. And being aware that dehydrated foods are not the same, I got a package of Good To Go's classic marinara with pasta to compare noodles to noodles, so to speak. Now, to be fair, their instructions do emphasize that the water should be boiling, all caps. Yes, boiling. You're also supposed to wait 20 minutes before eating, and it only gets worse at higher altitudes. Well, I had to try it pasteurized anyway just to see. I ran the exact same test setup, added 160-degree water as before, covered, and then thought about how big the universe is as instructed. Again, I shorted the water by about a quarter cup. After the same 6 minutes, I took a look. This time the mixture was still soup. Taking a bite, the noodles were still so raw they crunched like glass. Not even close. So I gave it another 6 minutes, and it became clear the stuff would go room temperature before it got hydrated. I ended up having to microwave it on high for 3 minutes and let that sit for another several before it was what you would call done. So, for freeze-dried meals, thumbs up. For dehydrated meals, fail. That bit about taking longer at higher altitudes got me curious, so I found this blog post by the Outdoor Herbivore. And based on testing and personal experience, they developed the following chart for additional hot soak time needed to rehydrate dried food at various elevations. Again, based on my own experience, I'd say that this only applies to reconstitution of dehydrated meals, and raw rice, pasta, stuff like that. They even have an asterisk at the bottom noting that extreme elevations can require the use of freeze-dried or instant meals. The only other real issue I could think of relates to a habit that many might consider the most important of it all. Hot drinks like your coffee or tea. As noted, 160-degree water is hot enough to burn if you stick your finger in it. But people can drink hotter stuff if it's in small sips. I'm more of an iced coffee person myself, so I looked around for an expert opinion. Obviously, you like what you like, but in case you've never sunk a thermometer in your coffee to say, that's the perfect degree, then this might give you a rough frame of reference from which to judge. The folks over at littlecoffeeplace.com say that above 175 degrees Fahrenheit, nobody's having a good time. It's too hot to taste, and you run the risk of burning your mouth. The range between 155 and 175 is for when you like it hot. It's a good steaming mug of brew that warms your hands and your insides, but many experts think that this is still too hot to accurately taste what you're drinking. It's more about the heat than the flavor at this level, and our pasteurized water is in this range. The Goldilocks range is from 140 to 155, and this is for the connoisseurs who want all the aroma and flavor without feeling like their coffee is tepid. And based on that, 160 degrees should get you where you want to be. But that's a serving temperature, not a brewing one. Here again, we have the same issue as with dried meals. If you're just dissolving instant coffee crystals, pasteurized water should serve a nice, flavorful, hot cup. But if you're actually brewing ground coffee in the field, that recommended temperature is between 195 and 205. Now, I'm guessing you could probably mix it a little stronger, wait a bit longer, and still get by, but that's not really my thing. For tea drinkers, Let's Drink Tea produced this nice infographic. It looks like you'd be okay with a few types and a little low on most of the others. It probably also depends on how particular you are. Okay, well, that's all I've got. In summary, boiling your water for safety is entirely unnecessary. It is orders of magnitude more pathogenic reduction than you need. And the official government advice to boil for 1 full minute is literally billions and billions of times in excess. Also, the conventional wisdom that heating fast saves fuel because you run your stove for less time seems intuitive, but it's false. A lower flame actually wastes less heat. So, combining the tactics of using an efficient flame level with a goal of pasteurization instead of boiling, you can actually cut your fuel expenditure in more than half. This can save you not just time, but weight, money, and the amount of canisters you need to recycle. And all you need to do this safely is a small, cheap, lightweight gadget that pays for its own weight in a single use. Alternately, you can use the Boil 3 Add 1 method. So pasteurized water, though not boiling, still rehydrates freeze-dried meals and makes a nice hot cup of instant coffee. Part 2 in this series on backcountry water treatment will address chemical methods from drops to tablets. As always, I very much appreciate your time, and thanks for watching. I found this interesting table compiled by the World Health Organization. It's basically a list of studies done for a variety of pathogens and their reported inactivation times and log reductions. It's a complete mixed bag in terms of temperatures tested and the way times and reductions are reported, so you have to be careful about how you sift through the data. We discussed 160 degrees Fahrenheit, which is 72 Celsius. Just cherry picking some of the entries at that temperature, you've got E. coli at 0.4 seconds per log and Salmonella at 0.1 seconds per log. Remember that bacteria are relatively easy to cook, and these studies seem to corroborate that pasteurization would be more than adequate. Viruses are the last to yield. For hepatitis A, there was no study reporting at exactly 72C. At 65C, we have 120 seconds for a 2-log reduction. And that's 1 minute per log, just as told by the folks at SCI during the WAPI discussion. There's also studies showing 5-log reduction in 30 seconds at 75C, which was about the temperature at which our green wax had melted completely during my test in the glass beaker, and that equates to 6 seconds per log. For Cryptosporidium, we've got a study showing 3.7 log reduction in 60 seconds at our target temperature of 72C, and that's about 16 seconds per log during pasteurization. All of this suggests that the WAPI scheme is indeed effective. And for Giardia, the WHO basically admits the data is limited. They calculated these numbers from 2 old studies, which I looked at. They weren't designed to investigate the type of information this table is meant to present, and they didn't make an effort to find lower limits for safe disinfection. And I looked around elsewhere, and oddly enough, I couldn't find anybody that had properly studied Giardia for its pasteurization temperature. Maybe that's because, at least according to SCI, it's one of the easiest to kill, being taken care of well before any bacteria or viruses that may be in the same water. And lastly, bear in mind that this is a list for international purposes. Some of these pathogens are fairly exotic by North American standards and not to be found in wilderness waters here. As I said, it's quite a mixed bag. There are higher and lower results, so I wanted to share the table so you can peruse for yourself.